forgot that. Okay, so let's look at the directional derivative here. Just quick review as what directional derivative is. Okay. So according to the definition, directional derivative is given a function f, okay? Well, you can use function two variables or three, but it doesn't matter. Then the directional derivative, the dd is df over ds. I should say a function of this and a direction u hat, okay, and s, a positive s is the displacement, okay, in u hat direction, okay, yeah. Then the directional derivative is basically df over ds in the direction of u hat, okay, and that equal to del f dot u hat, okay. That's directional derivative. Okay. If you want to say it in plain language, okay, so dd, directional derivative, is basically it's the rate of change in f, in this function f, okay, as walking in u hat direction by a small displacement or distance, okay, yeah, a delta s, for example, okay. So as you remember, when we draw the diagram, essentially you have a surface f at here, then you have a point here, and then you walk in the u hat direction, okay, by how much? Maybe by a delta s, right? Then correspondingly there is a change, okay, in this function f, okay. So that rate of a change is basically this directional derivative, okay. Yeah. So calculation-wise, it's fairly straightforward. Just calculate the gradient of the function f first, then do the dot product with the direction you're walking, u hat. Okay, that's it. That's directional derivative. As we in the last example we gave in the lecture, we said, okay, if you're walking in the positive I hat direction, right? If you're walking in the positive I hat direction, that's basically partial derivative f over x, okay? And if you're walking in the positive g hat direction, that's essentially the partial derivative, partial f over partial y, right? Yeah, it's all related. Okay. Of course, first of all, you gotta always remember, directional derivatives give you a scalar quantity. Okay, it's not like a grading vector. It gives you that grading vector is a vector. This is a scalar quantity. So, more important is let's review. Okay, based on the formula here, let's look at some properties. Okay, properties on this directional derivative. Okay. Yeah, the properties of directional derivative really give us quite a bit of information at here. Okay, so can you still hear? Is it too lower now? Yeah. So I can hear my own voice at here. Okay, so let's go back to the formula for the directional derivative. Just rewrite it here. Okay. Now this is a dot product, right? This is a dot product. As we learn in dot product, we have, if you look at the dot product here, basically what does that mean? You have del f is a vector. You have u hat, another vector right here. It's a unit vector. So you're doing the dot product. And according to dot product property, so what we do is, right, we calculate the magnitude of the del f, calculate the unit vector magnitude, then times what? Cosine theta, right? Times cosine. That's the definition of a dot product, basically. Okay? Yeah. So now, because the u hat is unit vector, so the absolute value right here is 1. So that basically brings us to this simplified formula. So del f magnitude times cosine theta, and theta is the angle between the two vectors. Okay? Yeah. Okay? So essentially, directional derivative equal to the grading vector times the cosine theta. And essentially, as I mentioned in the previous lecture, dot product here, particularly when you dot the unit vector, essentially what you're doing is you're calculating the projected length, right? You're getting the projected length of that vector in this direction u hat. Okay? Yeah. So then, based on this one here, we can summarize a few properties. Okay. Number one, if you look at this one here. Okay. Yeah. Under what condition that this directional derivative is a maximum value? So you look at this thing here. Under what condition you will have the maximum value? 0. What 0? Theta is 0, right? Yeah. So essentially, I would say when theta is 0, not just 0 actually. There should be another quantity, pi. Yeah. Okay. So when theta is 0 or pi, so we have this dd maximum. Okay, the maximum here. Just a second here. Maybe this is not right. Well, what value is cosine pi again? Negative ones. I'm saying a maximum, so I guess I shouldn't include the pi because there's a pi. Because pi is actually not maximum; it's actually what? Minimum. So if I say maximum, I should not see this. Okay? Yeah. So we have the directional derivative value maximum. Okay, we have this maximum here. So if it is maximum, and let's interpret this conclusion again here. Okay, when theta is 0, what does that mean? Because that basically means what? That basically means the del f and the u hat not just parallel, actually pointing to the same direction, right? Pointing to the same direction. So that means del f in the same direction as u hat. Okay, as u hat. So that essentially brings down to this conclusion of you want the directional derivative to be maximum, then your del f needs to be in the same direction as u hat. Or if the del f is in the same direction as u hat, then you have a maximum directional derivative. Is that clear? Right? So basically, either way works. Okay? Now, if you remember, when we learned grading vector, I specifically said one thing about the physical meaning, geometrical meaning of a grading vector. Grading vector pointing to the direction of what? Greatest increase of function f, right? I didn't prove you. But look at this one here. Well, that's basically the proof. When del f is in the same, when you're walking in the direction, see, this one here meaning what? When you're walking in the direction pointed by del f, you end up with maximum directional derivative. Or, in other words, you will end up with a maximum rate of change in function f. That makes sense? Right? So basically this is a short proof right here. Why grading vector pointing to the direction of the greatest increase of function f? Because from the directional derivative definition at here. Okay? Yeah. So, if the question is, what direction give you the minimum or the greatest decrease in function f? Pi. Exactly. So that's basically the second bullet here. When theta is pi, we have the dd minimum. In other words, right? So negative del f is the direction. Okay. In other words, negative del f is the direction of the greatest decrease in f. Okay, the direction of the greatest decrease in f. And the top one here, you can see that basically del f is the direction, okay, of greatest increase, okay, in f. All right? Yeah. So that simple formula really can bring these two important conclusions in here. There's a third one. So what happens when theta is pi over 2 then? Zero meaning physically means what? Perpendicular. And if you want to using neither decreasing or neither increasing, which basically means at that direction you have maximum. No. Yeah, well, okay. So so theta is pi. So this is del f, right? This is where del f is pointing to, and this is the direction of walking you had. So you're walking in a direction which is perpendicular to the greeting vector. So you're walking in a direction which is perpendicular to the greeting vector, and as you find it out, your directional derivative is 0. So 0 basically means the rate of change equal to 0. So in other words, when you're walking in a direction that is perpendicular to the greeting vector del f, is there any change in the function f? No. Okay? So basically in this case, there's going to be 0 change, okay, in function f. Okay? Yeah. Is that good? Yeah. So technically, if you're commanding, a troop, okay, to go along a 0 change in a certain terrain, so what do you have to do? You have to get the direction that is perpendicular to that greeting vector. Okay? Yeah. Okay, so remember this conclusions here, okay? So we'll do some exercise based on this based on the 3 bullets here. Let's just say this is the function f, okay, and we'll give a point here, -1, like this. I want you to find out, okay, first of all, starting from P0, okay, so you're starting from the P0 location, okay, yeah, walk to which direction that you will get the maximum increase in function f. Okay, so basically find out 3 different directions. Okay, maybe there could be 1 direction or 2 directions, so I'll just use brackets here. Find the 3 kind of directions. First direction is give you the greatest increase in f, then the greatest decrease in f, and then the third direction is that direction will result in 0 change in f. So when you're walking in that direction a little bit, okay, just a little bit, there shouldn't be any change there. Okay, like that. Okay, so all we need to do is we need to basically analyze based on the 3 bullets that are here. Okay, so I guess, either way, what we need to do is we have to calculate the grading vector, right? We need to calculate basically the grading vector at this P naught location first. Okay, so we need to know what this grading vector is. Okay, then we'll figure out the 3 different directions as required. Okay, so here's a function f. So calculate the grading vector. Okay, grading vector partial f over partial x is function 2 variables, partial f over partial x, partial f over partial y. So that's fairly straightforward. Partial f over x is negative 2x. Partial f over y is negative 4y. Then you plug in this P naught point into this grading vector. Okay? Yeah. So x equal to -1, y equal to -1. Once you plug it in, so the first one is what? 2. Second one is 4, right? So that's the grading vector. That's the grading vector at that location. Okay. So if I show you this one here, so this is basically roughly what the graph look like. So this is the f that equal to that function. Okay. And this is the contour plot. Okay, if you slice that using different levels of z plane. Okay, and that's the -1 location at here. Okay, and I believe that's the grading vector pointing to. Okay. Okay. So then back to the question number 1, 2, 3. Okay, we want the direction. So for number 1, we want the direction that results in the greatest increase in f. As we just learned, that direction has to be what? Has to be in the same direction as del f. So the u hat, right, is the same direction as del f at P naught. Okay? So you already calculate del f, right? You already calculate del f. All you need is a direction the same as del f. So what do we do? So the u hat will simply equal to, how do you get the u hat then? Yeah, exactly. Just normalize this guy, right? Just normalize that guy, okay? At P naught location, okay? Yeah. So normalize this. So 2, 4, 2 squared is 4, 4 plus 8. I think it's gonna end up it's a square root of 20. Was it right? 4 plus, yeah, square root of 28, which is 2 square root of 5, and normalize that, and then 2 cancel. So root 5, 1, 4. Okay. So that's the direction you have the maximum. Oh, sorry, 2. So that's the direction which will result in the greatest increase in function f. Okay, so second one, direction that results in the in the greatest decrease in function f. And it's pretty easy. It's what? It's basically the negative of u hat, right? So the second answer will be just simply negative u hat. Okay? So just negative. Okay, so it's a third one that might be a little bit confusing at this stage. Okay, but let's just see the third one. What's the third one? Third one is we want a direction that results in 0 change in f. So first of all, as we learned, what direction are we looking for? That direction has to be perpendicular to the del f, right? So we're looking for u hat perpendicular to del f. Okay, so mostly at this stage what you want to do is, u hat equal to x, let's just say, maybe I'll use AB here, okay? So I'm not sure what U hat is, so let's just define U hat as AB. Then, if U hat is perpendicular to del F, and then what do we do? That means U hat dot del F equal to 0, right? Equal to 0. Do we have del F? Yes, we do, right? That's 2, 4 there. So that's 2, 4. So basically this means A, B dot 2, 4 equal to 0. Or in other words, it's 2A plus 4B equal to 0. Okay? Yeah. Does that make sense? Yeah. Now, you have how many equations here? One equation, but how many unknowns? Two. So what can we do then? Right? Does that mean we have infinite solutions? Well, you have a del F here, so you have a del F. You're looking for, just hypothetically, you have a del F here. How many solutions would you have, just hypothetically speaking? You need a U hat. You need a U hat to be perpendicular to del F. So as a matter of fact, this is a function of two variables, so del F must be in the xy plane. Okay, xy plane. So you need a U hat perpendicular to del F. How many solutions would you have? How many? How many vectors can you draw that is perpendicular to del F? 2, right? Yeah, sorry. Are you wrong?
I was going to say that there are infinite, but in that plane there are only 2.
Yes. In the xy plane there will be 2. Right? So where are they? One is here, one is here, right? Okay? So technically you just have 2 solutions. You won't have infinite solutions at here. So what are we missing at here? We basically missed one requirement. Look at this. U hat is a unit vector, right? So the A and the B has to satisfy what? Equal 1. Okay? So we have these 2 equations here to solve for A and B. Does that make sense? Okay. Now this is basically very technical way to solve it, right? But now I want to show you a very intuitive ways to solve it. So first of all, we're looking for a U hat, right? Perpendicular to del F. Or in other words, the U hat must be perpendicular to the unit vector created by del F. Okay? Yeah. Now what's this one? I think we just solved that in part 1, which is this guy here. Okay? So in other words, let me try to write it in here. So U hat is perpendicular to this one. Okay? To this. So you need this is a unit vector already, okay? This is unit vector. Okay? This is unit vector. So what you need is, as we said, you need to find A and a B that satisfy the dot product equal to 0, right? So you need to find an A and a B such that A and B dot this one to be 0. Okay? So just by observation, okay, simply by observation, so 1 over root 5 times A plus 2 times B equal to 0. Observation, can you come up with an A and a B that satisfy this one to be 0 then? You have to come up with A and a B. Okay, there are 2 ways here. Just look at this one here, right? Make use of the information. So sorry, I missed one here, right? 2 over root 5. So what's A and B satisfy this? At the same time, and the A and B together give you a unit vector. Can you come up with a solution then? Just observing this one. So A is 2 over root 5, is that what you're saying? And then B is what? Negative 1 over root 5. Will that work? Yeah, right? And will the a squared plus b squared equal to 1? Check it out. Oh, actually, there's not 1, eh? What's going on here? Oh, yeah, it is 1. Yeah. Can you see that? A squared plus b squared equal to 1. Maybe if this is too much, let's do this way here. So u hat del f equal to 0, huh? Let's, instead of using this one here, u hat dot del f equal to 0. So which means that u hat dot 2, 4 equal to 0. So which means 2a plus 4b equal to 0. Get rid of that 1 over root 5, okay? Yeah, get rid of that 1 over root 5. That's probably too much. And also better yet, I'm going to get rid of the u hat. I'm going to just use a vector u, okay? To make it a more simplified thing here. Is that all right? Right? So if you have u hat perpendicular to del f, then any vector in the same direction of the u hat will also be perpendicular to del f, right? So now you have 2, 4 here. So look at this one here. What u can give you the dot product equal to 0? One solution is u equal to what? Negative 4. The other is 2, right? What's the other solution? It will be 4 and negative 2. Just based on this one here. Is that clear? See, 4 times 2 is 8, negative. 2 times 4 is positive, so plus together is 0, right? Then what's u hat then? What do? You basically normalize this guy here, right? Normalize this. You will end up with 2 directions, just like what you did here. So that basically end up with what? 1 over root 5, negative 2, 1. And the other direction is 1 over root 5, 2, negative 1. Okay? Yeah. So if you can, through observation directly, I think it actually shouldn't be that bad. That's fine. If otherwise, if you can't, then you follow through this mathematical relationship here to solve. Okay? Yeah, that'll also work. One of the assignments is a bonus question is basically you make use of this knowledge at here. Okay? Yeah. Is that good? Yeah? Did I confuse you? Yeah.
Just with this last one saying that the dot product is 0, does that mean that back on our graph, this direction is following the contour lines?
The u hat?
Yeah.
It's following the tangent line of the contour plot.
Okay.
Right? So, for example, this is a del f here, right? Then the u hat will be basically if this is a tangent line, either this way or that way there. Yeah. That will result in a 0 change in f. Is that right? That makes perfect sense because this is, what does this contour plot mean here? It means it's a plot representing the same level in the function f, right? Yeah. Okay? Very good. So as a matter of fact, we can also kind of explain it here. See, this is a surface, right? This is a surface, pointing down at it here, right? Now, remember the statement that the del f pointing to the direction of greatest increase. So you can sort of argue to yourself now, from the plot here, why does this del f pointing to that direction? Why not the del f pointing to this direction, right? Because you want to have an increase in the function f. So when you're going this way, guess what? You will have an increase, right, in the function f. Okay? Yeah. So that's sort of geometric explanations there. Any questions? All good? So regarding directional derivative, my requirement, okay, basically is the final exam, will be understanding the geometrical meaning, understand the physical meaning of this, and understand the 3 bullets Okay, so how do you properly find the directions? Okay, based on the 3 bullets there, the bullet points. Okay. And the next application, is, let's look at the so-called estimate change. Okay. Okay, let's look at estimate change in F. Okay, when walking along U hat by a small distance S. Okay, so you see, very basic ones is this. For scalar function y equal to f of x. Okay, often in time, what we're interested is how much of a change in function f as you are walking, or as you have a positive change in delta x, right, in x direction. So there is a change delta x. So the formula, as you remember, is basically delta f equal to the derivative, okay, of f, okay, at a certain location. So that's how you, I should put the approximate sign here. That's how you approximate the change, right, for a function of a scalar value. Okay, and as we are learning partial derivative, okay, we said if it's a function of 2 variables, it's a surface, then we can use a plane to approximate this surface. And at the end, we have a derived formula, so we can use this so-called total differential idea to approximate the change in function f as you have a change in delta x, as you have a change delta x, as you have a change in change of delta y. So that formula, if you remember, is delta f is approximately equal to fx, okay, at a certain point, and then delta x plus fy, x naught, y naught, delta y, right? Yeah, that's how we approximate this one at here. Okay, yeah. So let's focus on the second one and here. Okay, so you have to exercise this already. You had one of the question, if you remember the resistor, the question there. So for this one here, if I explain it in detail here, what it means is your original point is x naught, y naught. So now, where did it go? It go to x naught plus delta x and y naught plus delta y, right? So that's what it means here. So when you go from here to here, how much change in f? It's this formula, okay? Yeah. So in other words, if you draw something here, so this is x naught, y naught. And then this is x naught plus delta x and y naught plus delta y. Okay? Yeah. So basically you went from here to here. Okay? Yeah, you went here to here. So let's just say if this is a P naught point and this is a P1 point. Okay? It's a P1 point. Okay? Yeah. So now let's relate that to directional derivative now. Okay, do we learn directional? So if I go from here to here, then using vector concept here, what direction am I walking to? We're walking the direction, if I use a vector, it's P naught, P1, right? So that's the direction you're walking to. Okay? Yeah. Now what is the P naught, P1 then? P naught is this, P1 is this. So that's right. Exactly. So delta x, delta y, as Carl said, right? So this coordinate subtract this coordinate. Okay? Yeah. So that's the direction you're walking to. Okay? So essentially, you can get a u hat, right, out of this P naught, P1. That make sense? Yeah. Okay. Then the next question is, from P naught to P1, how much distance did you walk? So distance, so how much distance did you travel from here to here? So the distance, if I use ds to represent this distance here, maybe delta s, let's see. Okay, if I use delta s to represent the distance traveled, So technically, what are you going to do? You're going to use this, basically the coordinates of the coordinate of this, subtract this square, plus the coordinate of this, subtract this square, and then square root, right? So which end up with actually root. What would you get? Exactly, right? Delta x squared plus delta y squared. And that's essentially the magnitude of P naught, P1. Okay? Yeah. So, what I'm trying to say at here is, I'll give you for general formula next is, this formula that we have learned is actually very closely related, okay, to the directional derivative idea. Okay, directional derivative idea. Right? So this basically, I'll naturally bring it to the next bullet point here. So let's maybe, let's see, this is a first case scalar. This is a case when you have a function of two variable, and what's the delta f, right? So then the third bullet, let's take a look at the more general case. Okay, more general case, and we'll relate back to this one here. So more general case is the case I actually listed here. How much change in f when you are walking along u hat by delta s? Okay, so that's the general case that here. So for this case, what we need to do is, so we're saying how much change, right? Let's go back to the directional derivative. So how much change in f? What's going on here? Okay, it's kind of doing things by itself. This is a directional derivative. Okay, this is a directional derivative at a certain point, and that equal to delta f, okay, at p naught dot u hat. Okay, that's directional derivative. So then, how much change in f? So how much change in f when you are walking in the u hat direction by how much distance? By a distance or displacement of ds. See that, right? How much change this one here? So basically that equal to what? Equal to delta f p naught dot u hat. Okay, this is directional derivative times the not dot, okay, not dot, times ds. See, right? So this is basically the dd, and this is the displacement, okay, in u hat, okay, in u hat. So if you look at this formula here, there is a change in f, and how much is that? It's this one times the displacement that you walked along u hat direction. Okay, that's basically the answer to our general question at here. Okay, so general question. Okay, so whether this one makes sense or not, so let's use a specific, just not a specific example. Let's use this formula to test, okay, the second bullet at here, okay, to test this one. Okay, yeah. Okay, so as in the second bullet here, so just a sort of a quick proof at here, okay, just sort of quick proof here, not a very rigorous proof. Okay, so what we need is, right, we want to see, okay, so the ds, okay, as we find, what's the ds? ds equal to, where is that? ds equal to this one here, right? ds equal to this. So maybe I'll just rewrite this one here, okay? X naught, y naught to x naught plus delta x, and y naught plus delta y. Okay, so this is the case. You're walking from x naught, y naught location to a new point, to a new location. Okay, to a new location. Yeah. And then I'm gonna apply this formula. Okay, I'm gonna apply this formula. Let's check how much change in f if you do this. So what should we expect? If we apply this formula, we should expect to get where? To get this one here, right? To get this. Okay? Yeah. So let's do that. Okay. Then how much change are we going to get? So we're going to get roughly delta F equal to that formula. Okay. And times delta S. Okay. Times delta S. That's formula. Okay. Okay. So grading vector at the P naught location. Okay. And U hat. So grading vector is Fx at P naught, Fy at P naught, dot U hat. So what is U hat then? Well, let's go back to this one here. What is U hat? U hat should be the normalized what? The P naught P1, right? U hat should be normalized this one here. So normalize basically divide this quantity by the magnitude, right? The magnitude. So that's U hat. So U hat is delta x delta y divided by delta x squared plus delta y squared. Okay, that's U hat. Then altogether times the total distance that's changed along the U hat. What's the total distance change? As we just calculated, this is the total distance traveled, right? This is the total distance. So times delta x squared plus delta y squared. Okay, right? That's the formula here. So apparently you cancel this out, right? You cancel this out, and what do we end up with? Fx at P naught times delta x, Fy times P naught times delta y. See, that's exactly the formula that you used in calculating the function f change, right? When there's a change of delta x, delta y. Okay. So bottom line is the general formula at here. Okay. The general formula. What you need to understand in using the general formula is you need the grading vector, you need the direction of walking, and you need the amount of the distance that has changed along the direction of walking. Okay? Yeah. So let me give you a quick example right here, and then we can call off this directional derivative. Okay, so here's example. So function f is actually a function of three variables. Okay, y sine x plus 2yz. Okay, plus 2yz. Okay, so we have an initial point P naught 0, 1, 0, and going to the next point 2, 2, negative 2. Right? So you're moving from P naught to P1 by how much? By a distance, or by a 0.1 unit of distance. Okay? So don't be confused. Oh, what happened? This is the function 3 variables. Same thing, right? The previous function 2 variables, so you're walking in the xy plane. Now it's a function 3 variables, so you're going to walk in the 3D space. Okay? Yeah. So walk from here to here by this much of distance, 0.1 unit, maybe meter or centimeter, who knows, right? Yeah. Then let's estimate, right, the delta f equal to what? Okay. Essentially, it's a exercise of the formula that we just used. Okay, so I want to use this formula here. Right? If I use this formula, I have P naught. That's my starting point. That's great. Delta del f, we can calculate that. U hat, that's the direction walking. So we have to extract the information out of this given condition here. So how do I get U hat then? Well, we don't have U hat directly given, but we have P naught to P1. So the U hat should equal to P naught P1 divided by P naught P1. Okay? That's U hat. And back to this formula delta S, that's the distance walked in that direction. So as the question told you, so delta S should be equal to 0.1, right? Okay, yeah. So delta S should be 0.1 at here. Okay. Okay, so now you do the calculation, right? P naught, P1, so this point, subtract this point, that's 2, 1, negative 2. And then divided by the total, its magnitude. As you're gonna figure out, anyway, so you're gonna get this quantity. Okay, you're gonna get this quantity. So 2 over 3, 1 over 3, negative 2 over 3. Okay. Yeah. Is this clear? Okay. Yeah. So the next thing is essentially just plugging plugging into the formula. So let's calculate del F first. Okay, del F at P naught location. Again, it's partial derivative. So y cosine x, that's partial f over partial x, and partial f over y is sine x plus 2z. Partial f over z is 2y. And plugging P naught is 0, 1, 0. So x is 0, y is 1, and z is 0. So what does that give us? 1, 2, 0. No, sorry, no. What does that give us again? 1, 0, 2, right? 1, 0, 2. Yeah, 1, 0, 2. That makes sense? Yeah. Then the delta F, okay, the delta F is approximately, so this quantity, 1, 0, 2, dot U hat, dot this, times delta S times 0.1. Okay? Times 0.1. So that's equal to negative 2 over 3 times 0.1. So approximately negative 0.067 unit. Okay? Yeah. Okay, so that's typical example in terms of the directional derivative, estimated the change, okay, when there is a change in certain direction. Yeah. Is that right? Yeah. Any questions? So that's all about directional derivative, okay? Yeah. And I think that's every possible questions you can see. Yeah. Formula-wise, fairly straightforward. Okay. Any questions? All good? Okay, so now we move on to the next bullet points, which is mean and max. Sometimes I call it unconstrained Yeah, it's a bit of a, there's more to the unconstrained optimization, but anyway, it's the first step of that, mean and the max of a certain function f, okay, a function f. Okay. You actually learned mean or max of function, scalar function f, right, in the first year, okay? Yeah, but we're looking at is a multivariable function in here. So what does that mean essentially? I'm going to use you're going to use a function of two variables because we can graph that, right? So it's a surface. What does a surface look like? Maybe it's a surface, right? Maybe looking like this. Okay. Yeah. So you have up and downs of the surface, and you can see that apparently if people ask you is, okay, so where is the mean and the max, minimum or maximum location for this surface S? So you can tell them, oh, that looks like a peak, and that also looks like a peak, and this must look like a bottom, right? Yeah. So the question here is, when you compare these two, which one's big? This one, right? But if you restrict yourself just to within this location, then where is the peak? Here. Okay? As a matter of fact, there is a minimum here. But if you restrict yourself to this location, then that's the bottom here, right? If you restrict yourself to within this location here, then you ask the question, where is the maximum? So you're not going to give this, you're actually going to give what? Here, right? So basically, the question of this mean or max, there has to be more precise language here. So this one here, I would call it, okay, local, okay, mean, local max at here. Okay, local max. Now this one, okay, that's a trick one. Shall we call the local max, or in other words, it's called global max, right? So global basically means it's the maximum within all the boundaries that you're considering in here. Okay? Yeah. Now if this is not the boundary, the over boundary, you look at maybe there are some other boundaries here and here, right? Then at that point you wouldn't call it global. Okay? You would still call it what? Local. Okay? You still call it local. So, but for time being, for this one here, maybe I'll call it global. I will just consider the two right here. Okay? Okay? Yeah. And there is a local mean right here. Okay? For this one, and there is a within this boundary here, and there is a global. Okay? Global mean at here. Okay, global mean. So anyway, when we are looking for mean and max, so this concept of a local and a global that you have to bear in mind in here. Okay, you have to bear in mind. Yeah. Okay, so now the next question is, okay, how do we find those locations? Right? How do we find those locations at here? Now, it doesn't matter whether it's a local or global mean or max. Okay? It doesn't matter whether they're like this. As we learned from the gradient vector, at this location, the gradient vector at this location will all be 0, right? All be 0. So those locations, we're going to call them they're all locations very in common. So we call them critical location or critical point. Okay, so those are basically critical point. Okay, they're called critical. Why the critical points? Because the gradient vector at those locations are going to be 0. Okay, so there's another word called stationary point. Okay. So now that basically brings us to the first theorem. Okay, first theorem. We're going to try to find the locations of the mean and the max. But the first step to find the locations of mean and max is to find the critical points or the critical location. Okay? Yeah. So the first theorem is called first derivative test. Okay? Scalar function, you have the first derivative test, right? Scalar function, how do you find the critical point? The first derivative test has to be 0, right? Has to be 0. So it's the same thing now. First derivative. So what's the first derivative test then for local? Okay, this critical for the critical points. Okay, yeah. As we said, the critical point has to satisfy the grading vector to be 0. So that basically means the del f. Okay, maybe I'll put it here. If A, B is a critical point, okay, then the del f at AB is going to be 0. Okay, it's going to be 0. And the other way around is also works. If del f at AB is 0, then the AB is going to be a critical point. Okay? Yeah. So what does that mean then? We have a function of two variables, so function of two variables here, and expanding this expression in here will give us what's going to give us. So this grading vector, meaning fx, fy at this AB location is 0, right? So it's a vector equal to 0. Vector equal to 0 meaning the components of the vector must be 0. So that actually gives us two relationships. One is fx, okay, partial f over partial x at the location AB is 0. And the other is, okay, partial y at this AB is 0. Okay? That make sense? Yeah. So, first do this. First, this is the first derivative. Or in other words, it's the first partial derivative, right? Yeah, first order partial derivative. Okay? Yeah. Now, in this graph right here, okay, I graphed two very extreme cases, so maybe local minimum or local maximum. But if you remember in the lecture that we're trying to graphically show the function. So there is one particular function I graphed, if you recall that, which is what? Which is called a saddle, right? So the saddle basically means, for example, this is a saddle. This is a more extreme saddle. So that saddle point in this case is origin. And when you're walking in one direction, it's increasing. When you're walking in another direction, it's decreasing. It's very much like a scalar function. So this is a scalar function, y equal to x cubed. So the scalar function x cubed, if you draw it out, it's like this. And if you do the first derivative test, so first derivative meaning 3x squared equal to 0. That gives you x equal to 0. That's a critical point, stationary, right? And then, but from the graph right here, apparently this is not mean and this is neither max, right? Because when you go this way, it's increasing. When you go this way, it's decreasing. So we call that inflection point, right, for scalar point, okay? And in 2D case, it's called a saddle point, okay? Yeah. So that's basically the next objective now. If you do the first derivative test and you figure out some locations are critical, okay? Some location critical. But the question is that going to be a local minimum or local maximum? Or is it going to be a saddle, right? That's basically the second part that we need to figure out here. So this is a theorem 1. So let's look at this second theorem here. Theorem number 2. Okay. So theorem number 2 is a little bit more wording to write it here. Okay. It's more of like the second derivative test as a scalar. So we still call it second derivative test. But this is a more general second derivative, right? Compared to the scalar function. Function is one variables. Okay. Given function this, okay? Suppose that AB, okay, is a critical point if AB is critical point, as we just said, which means what? Which basically that's the first derivative test. This equal to 0. And this equal to 0. Right? Yeah, that's first derivative test. And then the following four rules, okay, will guide us in terms of whether it's a local mean, local max, or saddle. Okay, so the first one, the first rule is, so F is a local max, okay, at this A, B, okay, if fxx less than 0 and fxx fyy minus fxy squared greater than 0 at A, B. Okay? Yeah. So I'll use a scalar function to compare this, but for now I'll just write it down first. So f is a local max at this location if the second partial derivative, basically, okay, fx, that's the second order here, is less than 0, and this expression is greater than 0, okay, at this AB location. Okay? Yeah. And the second rule is then f is a local mean, okay, at AB if fxx is greater than 0, okay, and the same expression over the top there still greater than 0, okay, like this. Yeah. So that's rule number 2. And rule number 3, f is a saddle if this fx fyy minus fxy squared is less than 0 at AB. Okay, AB. Okay. So you got to read this carefully. Actually, you will have this formula because it's a bit of long here. I don't think anybody, you don't need to remember this, but actually you can remember part of that. So number 4 is, okay, so what happens if you look at this one here? Number 1, 2, 3 used what? Used this expression greater than 0, and then this expression less than 0. So the number 4 is, okay, actually the test is inconclusive. Okay, if the fx fyy minus fxy squared equal to 0. Right? That's the 4 rules, okay, we stick to for function with 2 variables. Okay. Yeah. If it helps you, you can, for this particular one here, okay, you can use this kind of a relationship. Create a matrix. And then calculate the determinant of the matrix. Okay? And that's basically this quantity. Okay? This quantity. In mathematics, this is only a function of 2 variables, but you can have a function of n variables. This matrix itself is called Hertzing matrix. Okay? And this is a determinant of a Hertzing. Okay? You heard of a Jacobian matrix, right? So if you take if you take Jacobian of the Jacobian matrix, you get this Hertzing matrix. So anyway, it's too complicated, but anyway, that's where that from here, okay? Yeah. But maybe what you can do is this. Think about the function of a single variables. When you have function of single variables, maybe let me write down here. Function of single variables, what's the Taylor series of a function of single variables? It's f of x. So Taylor series of functions single variables around x equal to x naught is this. Right, that's a Taylor series of function of single variables. So, back to the simple one, if you recall that, if I wanted to find the mean and max of single variables, I do what? I do first derivative test. Okay? So, first derivative test, and let the first derivative equal to 0, solve that, find the corresponding x naught location that gives you the first derivative 0, right? Then you do the second derivative test. So for single variable function, what if this guy is greater than 0? Would you have a mean or max for a single variable? This is greater than 0. Is a mean or max? Mean, right? Why is it mean? Because if this is 0 now, and this plus, this is already greater than 0. And you got another greater than 0. Basically, doesn't matter how you increase around x location, x equal to x naught location, your function f always have an increase, right? Always increase. So that basically means around the location you have a local mean. Okay? If this is less than 0, that means you will, at this x equal to x naught location, you will have a local max, right? So what happens if this guy equal to 0? It's inconclusive, right? You have to do higher derivative test, basically. Okay? Yeah. So that's a comparison here. Now you probably wonder now, oh, so that must means you must be able to do similar stuff for a Taylor series of function of two variables, right? That's exactly right. So this is actually out of the scope here. So if you're interested, everything I have written it here, okay, is actually will be explained based on Taylor series of a function of two variables. Okay? Yeah. If you're interested, you can come to me and I can show you how it's done here. Okay? Yeah. Is that clear? Yeah. So if you can look at the 4 rules here, then examples will be pretty straightforward. So let's look at an example here, okay, quickly. And how do we apply this theorem number 1 and 2 to find the local mean and local maximum of saddle points? Okay, so here's a function. This is a function of 2 variables, so it's a surface. Okay, yeah, and that's actually what this surface look like. Okay, it's like a butterfly, and here. Now let's find all the possible mean and max or saddle points for this particular surface. Okay, yeah. So step number 1. Okay, first derivative test. So what is the objective? What is the purpose of doing first derivative test? That's right. Try to find the critical points, right? Yeah. Try to find a point that we end up with this first derivative 0. So fx in this case, 24x squared plus 6y. Okay? What do? We set it equal to 0. And for this one here, we end up with y equal to 4x squared, negative. Okay? Negative 4x squared. And then we do Fy. And that's 3y squared plus 6x. Then we set it equal to 0. So we end up with, okay, we don't need to end up with anything now. So what do? We can substitute y equal to negative 4x squared into this one here. Okay, into this. Is that good? Right, two equations, two unknowns. They're not linear, but we can solve it. So sub this one here. So what do we got? 3 negative 4x squared plus 6x equal to 0. Okay. So that negative is gone. There's 4 is 16. So you can get rid of common factor 2. In the end, you end up with actually what? 16x to the power 4 plus 2x equal to 0. Okay, like that. You can get rid of 2 too, right? Or 8x to the power 4 plus x equal to 0. Okay? Yeah. So, up to here, common factor is x. Okay? Common factor is x. And this is basically what the x value satisfy this one here. So then, what's the solution? Apparently, there's one solution, x equal to 0. What's the other solution? That's right, negative 1/2. Right? Yeah. Good. So we have two locations give us this critical point. But x is not enough. We need a corresponding y, right? What's the y value at x equal to 0? So what do? Basically, we have the relationship here, right? So y and x satisfy this or this, doesn't matter. So y would be 0 at x equal to 0. And y would be negative 1. So if you plug in x equal to negative 1/2 over here, so y will be negative 1. So that's the location. There are two locations. Two locations we call the critical locations. Okay? Yeah. Then the next step is to use the theorem number 2 now, right? Second derivative test. Okay? So to do second derivative test, we can do this, okay, in a different way set here. For a 0, 0 point, so we look at differently. For 0, 0 point, what is fxx value? And what is fyy value? And what is fxy value? Okay? Yeah. So fxx, so you already have fx here. So fxx is 48x, right? 48x. 48x, maybe we'll write it down first. Fy is 6y and fxy is 6. Okay? So that's, in general, what fxx, fyy, and fxy is. So now, at the 0, 0 location, the fxx equal to, this is x here, is 0, right? It's a 0. And fyy is 0. And fxy is 6. Okay? 6. Okay. So at this location, that's the value of the second order derivative. And then we substitute into, we need to calculate this expression. What's the value of this expression here? So what's the expression? fxx fyy minus fxy squared. So that equal to negative 36, which is less than 0, right? Less than 0. So together, what's the current which is less than 0? Yeah, well, less than 0, actually, if you look at the rules here, what point is that? Saddle. It's a saddle, right? It's a saddle. Okay? So that means the 0, 0 is a saddle. Okay? Saddle. Is that good? So if I show you 0, 0, where is it? This is a 0, 0 here. Okay? That's a 0, 0. So you can see that as you're walking this way, you're kind of decreasing. As you're walking that way, so Anyway, right? You can see the directions determines the increase, decrease. So you can try out the other one for negative 1, negative 1/2, and negative 1 location. Okay? Now let's quickly do that. Fxx equal to 48x times this. So negative 24. Fyy 6y negative 6. Fxy 6. And what's the value of this? $108. Okay, 108. So greater than 0. So if you look at the rules there, Fxx in this location here is less than 0. So together, these two, this location is max. Okay? Was that good? Yeah. Okay, so that's basically wrap up with this this portion right here now. Okay, and then the next lecture, which will be after the Thanksgiving now, will be on the Lagrange multiplier. Okay.